What is the Large Hadron Collider and where is it located? The Large Hadron Collider, or LHC for short, is the world's largest and most powerful particle accelerator. It's like a massive scientific machine built to smash particles together at incredibly high speeds to see what they are made of and to explore the fundamental building blocks of the universe. Imagine a giant circular tunnel, almost 17 miles or 27 kilometers, buried underground near the border between Switzerland and France. That's where the LHC is located. At a place called CERN, which stands for the European Organization for Nuclear Research. Scientists from all over the world come to CERN to conduct experiments and try to answer some of the biggest questions in physics, like what gives particles their mass and what the universe was like right after the Big Bang. How does the LHC work? So think of the LHC as gigantic racetrack, but instead of cars, it is designed for particles called protons. These protons are accelerated to super high speeds, nearly the speed of light, in opposite directions around this huge circular track. Now, to get these protons moving so fast, the LHC uses powerful magnets to steer and focus the particle beams, and it has special sections where it gives them a push, like giving a skateboarder a series of strong pushes to keep them moving faster and faster. Once these protons are zooming around at top speed, they're directed to collide with each other at specific points. These collisions create a burst of energy and new particles, kind of like smashing two cars together to see the bits and pieces fly out. Scientists then use enormous detectors around the collision points to capture and study the particles created from these crashes. By analyzing the data, they can learn about the fundamental properties of matter and the universe. It's a bit like being a cosmic detective, piecing together clues about how everything works at the tiniest scales. What was the purpose of building the LHC? The LHC was built to help scientists answer some of the most fundamental questions about our universe. Here's a more relatable explanation. Imagine you have a really complex puzzle, but you're missing a lot of pieces. The LHC is like a tool that helps scientists find those missing pieces. Its main purpose is to explore the basic building block of matter and the forces that hold them together. One of the biggest goals was to find the Higgs boson, a particle that helps explain why things have mass. Without mass, particles wouldn't stick together to form atoms, and nothing we know like stars, planets, or even us would exist. Besides that, the LHC helps scientists investigate other mysteries like what makes up dark matter and dark energy, which we know very little about, but make up most of the universe. By smashing particles together and studying the results, the LHC lets scientists peek into the very small and very clear moments of the universe, giving us a better understanding of how everything works. What is a particle accelerator and why is it important in physics? A particle accelerator is a bit like a super high-tech slingshot for tiny particles. Imagine you have tiny balls like proton or electrons, and you want to fling them incredibly high speeds to see what happens when they hit something. That's basically what a particle accelerator does. These machines use electrical fields to accelerate particles to very high speeds, sometimes close to the speed of light. Then using powerful magnets, they steer and focus on these speeding particles. Finally, they smash them into each other or into a target. Why is this important for physics? Well, when these particles collide, they break apart and create a shower of even smaller particles. This allows scientists to peek inside the building blocks of matter. It's like smashing open a watch to see all the gears and springs inside, helping us understand how it works. By studying these collisions, physicists can uncover new particles, learn about the forces that hold everything together, even recreate conditions similar to those just after the Big Bang. This helps answer big questions about the universe's origin, structure, and the fundamental laws of nature. It's crucial for pushing the boundaries of our knowledge in the world of physics. What is the Higgs boson and why was its discovery significant? The Higgs boson is often called the God particle, but don't let the nickname throw you off. It's a fundamental particle associated with the Higgs field, which is an invisible field that exists through the universe. Imagine the Higgs field as a kind of cosmic molasses that other planets move through. Some particles get sticky and heavy, moving through these particles, while others pass through easily without gaining much mass. The Higgs boson is like the smallest piece of this molasses. Discovering it was crucial because it confirmed the existence of the Higgs field. Without the Higgs field, particles wouldn't have mass, and the universe as we know it wouldn't exist. The discovery of the Higgs boson in 2012 at the LHC was a big deal because it confirmed a major part of the standard model of particle physics, which is the theory that describes the fundamental particles and forces in the universe. Finding the Higgs boson was like finding the missing piece of a massive puzzle that scientists had been working on for decades. It opened up new pathways for understanding the universe and validated many years of theoretical work. How do superconducting magnets in the LHC function and why are they necessary? Superconducting magnets in the LHC are like superpowered electromagnets. To make them work, scientists cool them down to incredibly low temperatures, even colder than outer space, using liquid helium. At these super cold temperatures, the magnets become superconductors, which means they can create really strong magnetic fields without losing any energy. These powerful magnets are crucial because they help steer and focus the particles as they race around LHC's huge circular track. Think of it like guiding super fast cars around a racetrack with incredible precision. Without these magnets, the particles would fly off course and we wouldn't be able to make them collide in just the right way. By keeping the particles on track and speeding them up, these magnets make it possible for scientists to study the tiny bits of matter that make up everything in the universe. So superconducting magnets are a key part of what makes the LHC such a powerful tool for discovering new things about our world. What are the main differences between the LHC and other particle accelerators? The LHC, or Large Hadron Collider, stands out from other particle accelerators in a few ways: size and scale. The LHC is the largest particle accelerator in the world. Its circular track is nearly 17 miles long, or 27 kilometers, which is much bigger than most other accelerators. This size allows it to accelerate particles to higher energy levels. The LHC can accelerate particles to incredibly high energies, much higher than other accelerators. This is crucial for creating the extreme conditions needed to discover new particles and study fundamental forces. Superconducting magnets. Unlike many other accelerators, the LHC uses superconducting magnets cooled to extremely low temperatures to generate powerful magnetic fields. These fields are necessary to keep the particles on their precise paths. International collaboration. The LHC is a massive international project involving scientists from all over the world. This level of global collaboration is relatively unique and has brought together the brightest mind in physics. Surprising element. Did you know that the LHC is so powerful it can recreate conditions just moments after the Big Bang? This means every time particles collide, it's like taking a tiny peek into the very beginnings of the universe. Pretty mind-blowing, right? Data volume. The LHC generates an enormous amount of data, so much that the information collected from just one experiment could fill around 100,000 DVDs every second. This requires some of the most advanced data processing systems in the world. These differences make the LHC not just a bigger but a more powerful and sophisticated tool for exploring the mysteries of the universe compared to other particle accelerators. How do scientists analyze the vast amount of data produced by the LHC collisions? Analyzing the enormous amount of data from LHC collision is a monumental task. Here's how scientists handle it. Data collection. Each time particles collide in the LHC, they produce a massive amount of data. Detectors like ATLAS and CMS capture these collisions and record detailed information about the particles created. Data filtering. Due to the sheer volume, not all data is useful. Scientists use a process called triggering to sift through the data, filtering out the less interesting events and keeping only those that are likely to provide valuable insights. This helps reduce the data to a more manageable size. Distributed computing. The remaining data is processed using a global network of computers. This network, known as the Worldwide LHC Computing Grid, connects thousands of computers around the world. These computers work together to analyze the data, breaking it down into smaller chunks that can be processed in parallel. Advanced algorithms. Scientists use complex algorithms and machine learning techniques to analyze the data. These algorithms can identify patterns and search for rare events or new particles, making it easier to uncover significant findings. Surprising fact. Here's a fascinating twist. Sometimes the data analysis leads to unexpected discoveries. For instance, algorithms initially designed to search for certain particles have also been used to uncover new types of particles and phenomena, showing just how adaptable and powerful these tools can be. In essence, handling the LHC's data involves a combination of cutting-edge technology, global collaboration, and innovation techniques to make sense of the universe's most fundamental secrets. What role do particle detectors like ATLAS and CMS play in LHC experiments? Particle detectors like ATLAS and CMS are crucial components of the LHC experiments. Here's how they work. Detection. These detectors are giant multi-layered devices placed around the collision points in the LHC. Their main job is to capture and record the particles produced when protons smash into each other. They work like extremely sensitive cameras, snapping pictures of the particle collisions. Tracking. ATLAS and CMS track the paths of the particle created from collisions. They use different types of sensors to measure the particle trajectories, momenta, and energies. This tracking helps scientists determine what particles were produced and how they behaved. identification. The detectors also identify the types of particles produced. They use various materials and technologies to differentiate between different particles such as electrons, muons, and neutrinos. This is key to understanding the nature of the collisions. Data collection. The data collected by ATLAS and CMS is enormous. It includes detailed information about the particles' paths, energies, and interactions. This data is then analyzed to look for patterns and signals that could indicate new discoveries. Surprising fact, here's something intriguing. ATLAS and CMS are so massive and complex that their construction involved thousands of scientists and engineers from around the world, and they are so precise that they can measure particles smaller than the width of a human hair. ATLAS and CMS play essential roles in capturing and analyzing the data from LHC collisions, helping scientists explore the fundamental components of the universe. How do LHC experiments contribute to our understanding of dark matter and energy? LHC experiments play a significant role in our question to understand dark matter and dark energy, even though these mysterious components of the universe are elusive. Here's how. Searching for dark matter. Dark matter doesn't emit light or energy, so it's hard to detect directly. Scientists hope that by smashing particles together at high energies, they might produce new particles that could be dark matter candidates. If these particles show up in the data from the LHC, it would provide clues about dark matter. Testing theories. The LHC allows scientists to test theories about dark matter. For example, if certain theoretical particle predicted to make up dark matter are produced in collisions, it would support these theories. LHC's high energy collisions can help refine or rule out various dark matter models. Studying fundamental forces. Dark energy is thought to be related to the expansion of the universe. By studying fundamental forces and particles at the LHC, scientists can gain insights into the properties of the universe's expansion and potentially link it to dark energy. Surprising fact. Here's a surprising aspect. Some of the experiments and technologies developed for the LHC have unexpected applications in other fields like medical imaging. This cross-disciplinary impact can lead to new tools and methods for studying dark matter and dark energy. In summary, while the LHC doesn't directly absorb dark matter or dark energy, it provides a powerful tool for exploring theories and searching for evidence that could help solve these cosmic mysteries. Thanks for watching.